Hi everyone, this is SpaceX's Falcon 9 rocket, which is using the Merlin engine to combust kerosene and oxygen. Upon launch and re-entry, extreme heat is generated. But why don't rockets like this one melt? There are various methods for cooling, but the one that I'll be discussing today is the ablative method. Firstly, what do I mean by an ablative? In simple terms, an ablative is a material that lines the inside of a rocket combustion chamber and rocket nozzle, particularly in liquid propulsion, and it acts as a sacrificial layer to protect the underlying structure by reducing the amount of heat that is transferred. SpaceX's Merlin rocket uses a type of ablative called PICA-X, phenolic impregnated carbon ablator extended. It is a heat shield material that is designed to protect the rocket engine nozzle from the extreme heat generated during launch and re-entry. PICA-X is made up of carbon fiber weave that is impregnated with a phenolic resin, and so when it's exposed to heat, the resin chars and the surface ablates, carrying away that heat from the engine. So if we take a look at this slide, you can see the Falcon 9 rocket re-entering the Earth's atmosphere, and on the left is the surface of the ablative. In this caption, you can see that it can handle temperatures even as high as up to 2000 degrees Celsius. And this is a schematic of the ablation process. We'll go into this in depth a little bit more later, but just to show the main parts, we have the virgin material, which is essentially the main structure of the ablative. We have the pyrolysis zone. We'll also discuss this, but essentially that's where the material is decomposing. And you have this porous char here, which is very important for reducing that heat transfer, enhancing that heat transfer away from the rocket. And you also have the boundary layer of gases, which we'll also discuss. Carbon-based material generally has a strong reputation for its high melting point, large enthalpy of sublimation, and good radiation properties. Most materials used for ablative thermal protection systems are reinforced composites with organic resins as binders. And this is because organic resins such as phenolic offer high thermal stability, low thermal conductivity, lightweight properties, and adhesion properties. Before impregnation, the material begins as a simple carbon fiber insulator, which initially lacks ablative properties. But with the addition of the phenolic resin, the material attains ablator status while retaining the carbon fiber's original insulating properties. Because of Pica X's ability to withstand high temperatures, be lightweight, and exhibit controlled burning, it has been used successfully on several Dragon spacecraft missions, including the historic Crew 1 and Crew 2 missions to the International Space Station. Now let's just take a look at the importance of the structure PICA-X. Firstly, having a rough surface. The rough surface enhances heat transfer through thermal radiation and turbulence. It also increases surface area and therefore allows for more efficient cooling. We also have the random orientation of fibers and pores. And what this does is that it ensures that heat is dissipated evenly across the surface, preventing any hot spots from forming. Just note that if the fibers were all oriented in the same direction, then the material would be prone to cracking and erosion. So how does this all tie into what we're learning in Intro to Materials? This topic has chapter 5 of our textbook, diffusion, particularly non-steady state diffusion from the ablative. Before we get into the full-scale process, let's take a look at four main modes of heat and mass transfer. Firstly, we have heat absorption, where the shield absorbs the heat generated during the ablation process. This prevents heat from penetrating deeper into the underlying material. The next mode of heat transfer we have is thermal isolation. Well, thermal insulation, my apologies. After a process called pyrolysis, a layer of char forms. This highly porous structure exhibits relatively low thermal conductivity. By offering thermal insulation, it slows down the transfer of heat from the outside to the inside of the material. Next, we have mass transfer by way of gas ejection. This creates that boundary layer we saw earlier in that photo, and it is capable of absorbing heat and dissipating heat. Finally, we have erosion protection, and so the shield itself is sacrificial. As it erodes, it exposes that fresh material underneath to protect underlying structure from heat damage. So this is just a diagram of the rocket from launch, and then here is the re-entry, and so this is the ablation process that I'll be talking about. Again, this is an image of what the ablative looks like. Just to point out some key features, this is the gas boundary layer, the porous char area, pyrolysis zone, and the main air structure of the ablative. During re-entry, heat generated by friction between the spacecraft and the atmosphere is transferred to PICA X ablative via conduction. The phenolic resin in the PICA X matrix absorbs that heat and undergoes a chemical reaction that is going to release gases. These gases form the protective boundary layer of gas that thermally. So as the surface of the peak exablative material heats up further, it also emits radiation, and this is in the form of infrared energy. This radiation is absorbed by this surrounding gas layer and re-radiated away from the spacecraft, further reducing the amount of heat transferred to that underlying structure. This material forms a charred layer on the surface, and again acts as a thermal insulator and protects that underlying material from further heat damage. As the PICA X material heats up beyond its ablation temperature, it begins to burn away, releasing more and more gases that continue to form a protective boundary layer. This material breaks down via pyrolysis, which we had mentioned earlier. So pyrolysis happens when the heat causes material to break down into smaller molecules. These products are gas and heat and escape through that porous structure. And so, like we mentioned, that gas is creating that protective boundary layer and shielding from further heat damage. This cooling effect slows down that burning process. Note that the char burns in a controlled way over time because of pyrolysis, and eventually the char burns away completely and it's going to leave behind a thin protective layer of material. This sacrificial process is sometimes termed as thermochemical ablation. So this is a picture or a micrograph of a PICA sample, and I'm going to take you to the 3D model to show an attempt of how we represented this. So here's a 3D model. Please note that the pore structure should be randomly oriented, but this structure has angles at 60 degrees just to make it a little bit more clear. And so if you look through, there are actually these little gaps away from like between these spheres. And as we mentioned before, it allows for heat dissipation. This acts as a convective portal for that heat to be dissipated evenly away from the ablative surface and also helps in absorbing heat as well. It's also cool to note that the density of PICA X only needs to be about 0.3 grams per centimeter cubed and only a thickness of 6 centimeters to protect the spacecraft from intense heat during reentry. And as mentioned before, it can protect like against temperatures as high as 2000 degrees Celsius. And so what this does is that it keeps the interior of the capsule at like room temperature. And so all of these features allow for the faster re-entries and the ability to shield from those higher temperatures and overall ease of production. That is the end of my presentation. Here are the references, and I'm open to any questions you may have. Thank you so much.